This is lecture 4I, and today we're going to talk about molar masses and stoichiometric conversions. We've calculated molar masses of compounds before, and as an example, we're going to calculate the molar mass of ethanol, C2H5OH. If you want the mass of 1 mole of ethanol, you have to recognize that 1 mole of ethanol contains 2 moles of carbon. It actually contains 6 moles of hydrogen, 5 plus 1, and 1 mole of oxygen. So we're going to determine the mass of each of those. 2 moles of carbon would weigh 2 moles multiplied by 12.01 grams per mole, or 24.02 grams. 6 moles of hydrogen would be 6 moles multiplied by 1.01 grams per mole, giving us 6.06 grams. And the 1 mole of oxygen would weigh 16.00 grams. If these are the masses of the different components of 1 mole of ethanol, then if we add them up, we're going to get the molar mass of 1 mole of methanol itself, which is 46.08 grams. The significance of that number is it tells you how many grams you have to measure out on a balance to make sure you have 6.022 times 10 to the 23rd ethanol molecules, which is called a mole. So it gives us this equality statement: 46.08 grams of ethanol equals 1 mole of ethanol. And the most significant thing about that conversion factor, or that equality statement, is it allows us to convert between grams and moles for any chemical substance. So now we're going to calculate the number of ethanol molecules in 25.0 milliliters of pure ethanol, which is a liquid. The density of the ethanol is 0.789 grams per milliliter. So in this problem, if we're going to start with 25.0 milliliters, which is the volume of pure ethanol, we've seen in previous problems that if you want to convert volume into mass, you need to know the density of the material, which is given here in the problem, 0.789 grams per milliliter. That density tells you a conversion factor or an equality statement, much like molar mass did in our previous problem. It says 0.789 grams of ethanol equals 1 milliliter of ethanol. So this can be used as a conversion factor between milliliters and grams, grams and milliliters. So in this particular problem, if we're given the 25.0 milliliters of ethanol, I can use the density to convert this from volume into mass. And I would arrange it with 1 milliliter of ethanol on the bottom and the 0.789 grams of ethanol on the top. This allows the milliliters to cancel out. The reason we do that is that we can now convert grams into moles. We do that with the molar mass of ethanol, which we had calculated previously, arranging the molar mass with the grams in the denominator, 46.08 grams of ethanol below, 1 mole of ethanol on the top. This allows us to now determine the number of moles of ethanol in this 25 milliliter sample. If you ever have the number of moles then of a particular material, you can calculate either the number of atoms or molecules, depending upon what kind of substance it is. And this is a molecular substance, so it'll be the number of molecules. The number of molecules of ethanol will have to be determined from the conversion factor. 1 mole of ethanol equals 6.022 times 10 to the 23rd molecules. The mole goes in the bottom to cancel out, molecules on the top. We're multiplying a 3 significant figure number by a 3 significant figure number divided by a 4 significant figure number multiplied by a 4 significant figure number. Answer will come out 3 significant figures. And so we can actually determine that 25 milliliters of ethanol contains 2.58 times 10 to the 23rd molecules of ethanol in it. Let's try this. Let's calculate the number of carbon atoms in a 10.0 milliliter sample of pure ethanol. Similar to the last problem, only now we're not trying to calculate the number of ethanol molecules, we're trying to calculate the number of carbon atoms, and let's show you how we wind up doing that. If we start with the volume of the ethanol, which is given in the problem, 10.0 milliliters, we can convert this into grams by using ethanol's density. From the previous problem, that was 0.789 grams per milliliter. So arrange it with the milliliter on the bottom to cancel out, and now we know the mass of this ethanol sample. We can now use the molar mass of ethanol to convert grams into moles. I'll put the 46.08 grams on the bottom and the mole of ethanol on the top, and we've now calculated moles of ethanol just like we've done before. Now, here's the point where we want to look at what we're trying to solve for. We're trying to get carbon atoms. We have moles of ethanol. From the formula of ethanol, I can determine an equality statement between how many moles of ethanol and how many moles of carbon there are. We did that when we were doing the molar mass calculation. 1 mole of ethanol contains how many moles of carbon? 2. So I can write an equality statement, 1 mole of ethanol is equivalent to or contains 2 moles of carbon, and this is how I convert from ethanol into carbon. If I now know how many moles of carbon there is, and carbon's an atomic substance, then I can use Avogadro's number to tell me 6.022 times 10 to the 23rd carbon atoms equals a mole of carbon. And if I arrange it so the mole will cancel out, I can multiply through now, and I'll determine the number of carbon atoms in this 10.0 milliliter sample of ethanol. This comes out 2.06 times 10 to the 23rd. Let's calculate the number of ethanol molecules in 45.0 milliliters of 80 proof vodka, and the density of the vodka is 0.92 grams per milliliter. Some of you may not be able to do this problem because you may not be familiar with this term proof. When you get to be 21, you'll find out that that's one way to measure the alcohol content in an adult beverage. And when you see the proof of an alcoholic drink, if you divide that number by 2, that tells you the percentage of alcohol in that particular liquor. So 80 proof vodka means that vodka is 40% alcohol by volume. And if I write that as an equality statement, 80 proof vodka equals 40% ethanol by volume. That's what proof means. So you could have something as high as 200 proof. That would be 100% ethanol. Now, this is by volume. So let's do this. If we had, let's say, 100 milliliters of vodka, and we know it's 40% ethanol by volume, 100 milliliters of vodka would contain 40 milliliters of ethanol. So that's an important relationship we can derive from that particular data about the proof of the vodka. So let's see if we can calculate the number of ethanol molecules. We're starting with 45.0 milliliters of vodka. Vodka is the name of a mixture. It has water and alcohol and who knows what else is in there. So I can't convert, well, I can actually convert milliliters of vodka into grams of vodka with its density. But if I were to do that, because vodka is a mixture, there is no molar mass for a mixture. I can't convert grams of vodka into moles of vodka. I can convert a pure substance from grams to moles. A pure substance has a formula like sodium chloride or ethanol or water or oxygen. But vodka is a mixture. I can't do that. What would be better for me is to convert this milliliters of a mixture into milliliters of a pure material. And that's where I'm going to use the equality statement in green. 100 milliliters of vodka equals 40 milliliters of ethanol. So if I put the 100 milliliters of vodka on the bottom and the 40 milliliters of ethanol on the top, now I've converted from a mixture into a pure substance. And now that I know there are 40 milliliters of ethanol, I can convert the volume of ethanol into mass of ethanol if I know ethanol's density. So I'm not going to use the 0.92. That's the density of the mixture called vodka, which is a combination of alcohol and water. I need to go back to the previous problem and get the density of ethanol, which was 0.789 grams per milliliter. Arranging it this way, the milliliters cancel out, and now I've calculated how many grams of ethanol there are in this vodka sample. If I know grams of ethanol, I can now convert it into moles by using ethanol's molar mass with the grams on the bottom, moles on the top. And if I know moles of ethanol, this is a molecular substance, I can use Avogadro's number. 1 mole of ethanol always contains 6.022 times 10 to the 23rd ethanol molecules, and arranging it this way so the moles cancel out. Multiplying through, if you notice in this case, I'm multiplying a 3 significant figure number by a 2 significant figure number by a 3 significant figure number divided by a 4 significant figure number multiplied by a 4 significant figure number. The least number of significant figures was 2. My answer will need to be rounded to 2 significant figures. And so this vodka contains 1.9 times 10 to the 23rd molecules of ethanol. Let's see if we can calculate the mass of just one ethanol molecule in grams. So if you're going to convert 8 moles of ethanol into grams, you start with 8 moles. If you're going to convert 1 molecule of ethanol into grams, start with 1 molecule, and then go, what can you convert molecules into? And the only type of equality statement we know that includes molecules is the Avogadro number equality statement. 6.022 times 10 to the 23rd molecules equals a mole. So I'm going to use that, arrange it with the molecules on the bottom so they'll cancel out, mole on the top. And if we do this, we're calculating how many moles of ethanol there are if you have one molecule. If my units are now moles, I can switch moles into grams by using the molar mass. Mole on the bottom, 46.08 grams on the top, moles cancel out, and if I multiply this through, then I'll have the number of grams that one molecule of ethanol weighs. The one molecule was a counted number, so I'm actually multiplying and dividing by a pair of 4 significant figure numbers. So my answer will come out 4 significant figures, and I get one ethanol molecule weighs 7.652 times 10 to the minus 23rd gram. So with this technique, you can calculate the mass of one molecule, one atom of any substance that you may be interested in. Let's look at another stoichiometric relationship. Let's say a metal oxide has the formula M2O3 and it's 29.0% oxygen by mass. Calculate the molar mass of metal M. When you're given percentage data, you're not actually given any physical numbers, and so you can always assume that you have, let's say, 100 grams of the material if the percentage is by mass. So if you have 100 grams of the compound M2O3 and it's 29% oxygen, that means it's 29.0 grams of oxygen, and the rest must be metal M, which would be 71.0 grams. That's going to be important, because in this problem, we're trying to calculate its molar mass. And in many of the molar mass calculations we've done in the past, you have to think about what the units are of molar mass, grams per mole. So if you want the molar mass of metal M, you're going to need the grams of metal M and divide it by the moles of metal M. Well, if we're making a fictitious sample of this compound M2O3 that weighs 100 grams, that we know is 29 grams worth of oxygen, it must be 71.0 grams of M. So I know the numerator in this calculation. What I need to solve for is how many moles there are. So if we want to try to figure out how many moles of M there are, the only other number in the problem we know is that it would be 29.0 grams of oxygen in this fictitious 100 gram sample. So if I take the 29.0 grams of oxygen, I can convert that into moles. Now, look what we're trying to calculate. We're trying to calculate moles of oxygen atoms because the formula says 2 M atoms and 3 oxygen atoms. So I'm trying to calculate the moles of oxygen atoms. Oxygen may be diatomic in its elemental state, but it isn't in this compound. And I don't want to know how many moles of diatomic oxygen molecules are in this compound. I want to know how many moles of oxygen atoms. So I use the molar mass of 16.00 grams of an oxygen atom equals 1 mole of oxygen atoms. I now know how many moles of oxygen there are in the sample. I need to get to moles of M, and if you look at the formula of the compound, it's going to tell you the equality statement you want to use. Just think about how you would calculate the molar mass. What is this telling you? You have 2 moles of M in the compound and 3 moles of O. So the equality statement you can use is 2 moles of M equals 3 moles of O. And I'm going to arrange that as a fraction with the moles of O in the denominator, so they will cancel out. And I will calculate now theoretically how many moles of M must have been in this compound. And that comes out 1.208 with the guard digit moles of M. So now I can go back to my molar mass calculation. I know the compound, my 100 gram sample, is 71 grams of M. If I divide it by the 1.208 moles of M, you can calculate what the molar mass of the metal is. And if another question asked you what metal do you think it was, you would look on the periodic table and try to determine the elemental metal whose molar mass is closest to 58.8. One final type of calculation I want to talk about are theoretical percent compositions of compounds by masses. And we'll do this as an example. We're going to calculate the percent composition by mass of sodium nitrate. So what they're asking in this problem is the compound sodium nitrate, which you need to know its formula. Sodium is Na+1, nitrate is NO3 -1, so the formula would be NaNO3. If you have any sample of this compound, what percentage is it by mass sodium, what percentage is it by mass nitrogen, and what percentage is it by mass oxygen? The question involves 3 different answers. So the percent for Na, percent for N, percent for O. You can do this if you just set up the calculation to determine the molar mass of the compound. When we do that, all of a sudden how we get the percentages by masses are going to appear right before our eyes. So let's do that. To calculate the molar mass of sodium nitrate, it has 1 mole of sodium in it. So I go 1 mole of sodium multiplied by 22.99 grams per mole. 1 mole of this compound has 1 mole of nitrogen, so I'm going to go 1 mole of nitrogen multiplied by 14.01 grams per mole, so it contains 14.01 grams of nitrogen. And 1 mole of sodium nitrate contains 3 moles of oxygen, so 3 moles of O multiplied by 16.00 grams per mole gives us 48.00 grams. If you add this up, this is going to be the molar mass of the compound. So 1 mole of this compound weighs 85.00 grams. But here's the visual thing now. If 1 mole of it weighs 85.00 grams, 22.99 of that is sodium. So 22.99 grams out of the 85 grams is the fraction that's sodium. So if you go 22.99 divided by 85.00 and then multiply by 100, you'll have a percent by mass. So we calculate the percent by mass of sodium by going the total mass of sodium in 1 mole of the compound divided by the mass of 1 mole of the compound, which is its molar mass, multiplied by 100. They're both 4 significant figure numbers. That comes out 27.05%. To do the same thing for nitrogen, you look at the formula or how we calculated the molar mass, and out of the 85 grams for 1 mole of the compound, 14.01 of that is nitrogen. So I'm going to take 14.01 grams of nitrogen divided by 85.00 grams of the compound, multiply by 100, both 4 significant figures, and that'll actually give you the percentage of nitrogen in this compound. There's only one element left, so a shortcut way to do the last element, it would have to be 100% minus 27.05 minus 16.48, account for the rest of it. Or you could do it the same fashion we did. The amount of oxygen that's in 1 mole of the compound is the 48 grams. So the fraction of oxygen in 1 mole of the compound is 48 grams out of the 85 grams, both 4 significant figures. When you multiply by 100, I get 56.47%. So we've done this based upon the actual formula of the compound and its calculated molar mass. So these are called theoretical percent compositions. We could also do this experimentally, and that'll happen in one of our experiments during the semester here. But this is how you would actually do that theoretically. I want to do one final theoretical calculation. Let's calculate the percent by mass of water in barium chloride dihydrate. When you see that name, dihydrate means there are 2 water molecules bonded to each formula unit of barium chloride, which is BaCl2. The way you'd write the formula for that hydrated substance is BaCl2 dot 2H2O. And we could calculate the percentage of barium, the percentage of chlorine, the percentage of hydrogen, the percentage of oxygen in this particular compound by mass. But this particular problem is asking for the percent by mass of water in barium chloride dihydrate, which is a common type of calculation. So we're going to do it similarly to the last problem. We're going to determine the molar mass of the compound. And when you do that, you have to realize those water molecules are actually in the crystals. So when you calculate the molar mass of barium chloride dihydrate, you have to count the barium, the chlorine, the hydrogens, and the oxygen. So this compound, 1 mole of it, contains 1 mole of barium. So that's 1 mole multiplied by 137.33 grams per mole. It contains 2 moles of chlorine. So that would be 2 multiplied by 35.45 grams per mole. That gives 70.90. And then because that coefficient 2 there is in front of the H2O, if you went 2 times 2, there would be 4 moles of hydrogen, and 2 times 1 would be 2 moles of oxygen. And you can finish the calculation by doing 4 moles of hydrogen times 1.01, 2 moles of oxygen multiplied by 16.00. But because I'm trying to calculate the percent by mass of water in the compound, what I'm going to do, I'm going to calculate in my head the molar mass of water. 1.01 plus 1.01 plus 16.00 is 18.02 grams per mole. And there are 2 moles of water in the formula. So I'm going to go 2 moles of water multiplied by 18.02 grams per mole. And so I can clearly see now how many grams of water there are in 1 mole of this compound. If I add all those numbers up, that's going to be the mass of 1 mole of the compound. And now to calculate the percentage of water, the fraction should be apparent here. it's 36 grams of water out of the 244.27 grams of the entire compound. So your percentage of water will be 36.04 grams of water divided by 244.27 grams of barium chloride dihydrate, and then multiplied by 100. I've got a 4 significant figure number divided by a 5 significant figure number, so my answer will be rounded to 4 significant figures. And so we can theoretically say that barium chloride dihydrate contains by mass 14.75% water.